Thank you very much, and thank you very much for the invitation to come here to Bonn and to spend some time here. So what I want today to talk about today is quite Riemannian, I'm afraid, though it will deal with singularities. So the interesting objects in the end are not regular things. But to start out with, what I want to talk about is a very basic energy, just the Dirichlet energy of maps from surfaces into Riemannian manifolds. And I want to talk about quantitative estimates, the quantitative analysis of PDEs. So roughly speaking, what I want to talk about is whether almost solving a problem, that is almost solving a PDE or almost minimizing something, almost gives you a solution. And I want to talk about whether you can make this precise really with quantitative estimates, as in how far off are you from the nearest true solution if you know that you solve the problem up to a small epsilon. And the sort of 10-second version of the talk is life is good if everything is non-degenerate and non-singular, and life becomes interesting if anything singular happens. And a lot is not known in that situation. So I want to split up this talk into just a bit of a basic overview first about what is quantitative theory of PDEs about, what are the questions you might want to consider, before talking about the Dirichlet energy form a little bit, and then bringing this together to talk about what we can actually prove in this situation. So let me start with a bit of motivation. And just with sort of the basic questions. So for me, my favorite energy is the Dirichlet energy. That's why it's already written up. I assume not everyone will agree with me that this is the best possible energy in the world, and that maps from surfaces to manifolds are the best thing in life. So probably everyone has a different opinion, and just take your favorite energy. So take your favorite quantity, I just call it E for simplicity, on your favorite set of objects, your favorite set of admissible objects. Say this goes into, I mean, life is positive, right? Oh, we want it to be positive, so let's take a positive quantity. Given such a set, of course, we're interested in the critical points. So let me denote them by script C, the set of U, which are critical points. So the gradient vanishes. And let me take the M, the minimisers. So the energy of U is equal to the infimum of the energy over the admissible set. And I just want to write this for short as E min. And then I'm also interested in the behavior of the critical points with respect to their energy. So I want to write big psi of E to be the set of energies E of U, so that U is a critical point, so the critical values. And now you can ask a number of very basic questions about this. So basic question, first of all, of course, is do these objects exist? Are they unique? What properties and so on they have? But I do not want to talk about this, but I want to talk about related almost solutions. So the first question I want to ask is, does U almost critical imply that U almost a critical point? And you can ask such questions at two levels. On one level, at the level of compactness, or sometimes also you can call it the qualitative level. As in, do I know that if the norm of the gradient of Ui goes to 0, Ui is maybe bounded energy or something like that, norm taken in a suitable way, that's part of the problem, what the right thing is, does this imply that the distance of the Ui's to the set of critical objects go to 0? Now that's of course the starting point to understand anything to do with almost solutions, but often that is not enough. You basically want to say, does it go to 0 and how fast? In terms of, if I know how fast this goes to 0, can I say how fast I approach the set of critical points? So the quantitative version is, does there exist some exponents, and I'm going to call them gamma 1, gamma 2 positive, such that I can bound the distance of the UIs, or let me first start with the energies of the UI to the set of critical values by a norm of the gradient to some power. I don't even need UI here. And similarly, can I bound the distance of my U to the set of critical points in terms of a power here? And of course, when I say distance, it should be a distance which is relevant to your property, to your energy. So for me, if I consider the Dirichlet energy, the natural distance I want to consider is the strongest where I have a chance of controlling things, and that would be Sobolev H1 distance. So that's the basic question when you're looking at critical points. Now, you can do the exact same thing for almost minimizers, and you just reformulate the corresponding problem. So 2 is about almost minimizers. You can do the same thing at the qualitative level. So does the energy of UI converges to E min ensure that the distance of the UIs to the minimizing state go to 0? And then at the quantitative level, can I bound, say with some exponent gamma 3 positive, can I bound the distance of any map U with some maybe bounds on something, maybe nothing at all in my admissible set? Can I bound this by a power of the energy defect to the gamma 3, where delta U is just short for energy of U minus minus minimal energy? So these are the basic questions I want to consider. Now, people do not agree how these questions should be asked, should be called in the literature, which makes Googling quite challenging, in particular across communities. So the first type, almost critical, implies almost a critical point. In the geometric analysis community, you would call this Wojciechowicz estimates. In the more pure PDE community, you would call it quantitative stability estimates for critical points, or quantitative rigidity estimates for critical points. And then you would call 2 probably quantitative stability or rigidity estimates, as you like, for almost minimizers. And so let me call this thing here M. Okay, now it's sort of 9 o'clock, so let's start with a simple example. And I promise it's a simple example. So let's have a warm-up to just get some intuition. Now, what's the simplest energy in the world that is interesting? I would say that E of t is t squared, t in the reals. I hope we agree that's a simple example. This is not quite general enough for what I need. I need it more general. I want C0, Z0 positive. Okay, so this actually gives you a really good picture of what the best case scenario is for these estimates. So let's look at this in this situation. So of course we have delta of t is just the same as E, C0 dt squared. The size of the gradient of t is 2C0 t, and the distance is just t, whether it's from the critical points or from the minimizers. So that tells us that the first type of Wojciechowicz is okay with exponent gamma 1 equals 2. So I can bound differences here of energies. So Wojciechowicz 1 is the distance of the energy to 0 is bounded by gradient squared. That's the optimal case. If I'm looking at the distance to the critical points, that scales like t is bounded linearly in the gradient. So gamma 2 is 1. And then the minimizing estimate this is okay with gamma 3 is equal to 1/2. And if you do a little bit more work and check out with what powers the C0 appear, we have this with constants C, which shoot up to infinity as C0 goes to 0. And morally speaking, if you have a map which has basically this parabolic behavior depending on how steep the valley is and whether it's a parabolic valley rather than a t to the 4 valley, that's sort of the thing you should expect to get. And so just based on this intuition, what you should expect is for nice problems, we basically expect that such Wojciechowicz and stability estimates, they hold with these exponents if the second variation of the energy is definite, orthogonal to the set of critical points, respectively the set of minimisers, because if I take this energy and make it much more general, as in I consider it just on Rn, and I'm considering T1 squared, and I'm ignoring everything else, of course nothing changes. So the null, the critical point directions, they shouldn't really influence my problem. It should just be the behavior orthogonal to the critical points. And of course the critical points, reasonably we expect them to be a finite dimensional set. So we're expecting if this Hessian is definite orthogonal to the relevant set of critical points or minimizers, I should basically expect this with a constant C that depends on the eigenvalue gap. At lambda equals to 0. And that's a pretty good sort of approximation to real life. It's also the case that if d squared E is degenerate, but we have still polynomial behavior. So if I take my energy and I swap my 2 to a 4 or similar, I'm still getting the same type of results, just with smaller exponents. So basically, if I have degenerate, but E is analytic, then I should expect the same estimates with smaller exponents. So that's just sort of the intuition of what should you expect. Now, why do we care about any of this? So we care about these things, first of all, just from a practical viewpoint, because understanding almost critical points is important when you solve problems. In particular, often your problem is just modeling something. Your problem is not the exact thing you want to solve. So the question of whether a bound on error gives you a bound on distance to what you want is really important. Also, let me remark that these estimates are related to other problems. So remark that in particular the Wojciechowicz estimates are closely related to behavior of gradient flows. And in particular with respect to like uniqueness of limits at t equals infinity. If you have a gradient flow whose solution exists for all times, if you get a Wojciechowicz estimate of the first type, here with a gamma 1 strictly greater than 1, you're guaranteed that it converges to a limit, at least at the polynomial rate, in the case of the optimal exponent, even at an exponential rate. And then in addition, they are also really helpful with respect to uniqueness of blow-up models. So in the study of mean curvature flow, for example, in work of Kolding Minicozzi, they are using these Wojciechowicz estimates to control these things. And of course, they're also related just to the behavior of the energy spectrum. Okay, so I said this is sort of the warm-up, this is the expectation. Let me just make a few remarks. So this whole study goes back to the work of Wojciechowicz. So basically they're due to Wojciechowicz in the 70s. So key results in this context. And then by Leon Simon, who extended this in 83 to PDEs. So the proof of Wojciechowicz is just for finite dimensional settings. And basically what he established is that Wojciechowicz estimates hold for any analytic function on Rn in a neighborhood. And this is a really deep proof from algebraic geometry that I think most analysts don't understand, but we're really thankful that the paper is written in a way that the results are really well understandable. Then the work of Leon Simon is on energies, which are just sort of the typical Lagrangian. So let me just write this up for a moment. So this is work of Simon from 83. And it basically tells you that if you have an energy of u, which is just an integral of a Lagrangian L of u grad u x dx, where L is analytic and it's convex in the gradient. So basically what you need is that the Euler-Lagrange equation should have a nice elliptic form. So then for every critical point, there's a neighborhood such that if my map is close to u star, then I have a Wojciechowicz estimate. So L1 and L2 hold. And this is for all u, so that u minus u star is less than epsilon, and it needs to be in a pretty strong form. So in the original paper of Simon, it's a C2 alpha closeness. You can do a little bit less, but basically what it tells you is if you have a single critical point, around this critical point is a little neighborhood, so that if you're basically converging strongly to that critical point, you can apply Wojciechowicz estimates. And in particular, this is not applicable if you have maps which form singularities, because they will not be in an epsilon neighborhood. And let me also remark that this epsilon here, this shrinks down if anything bad happens, like if your eigenvalue gap shrinks to 0, and that's very typical of singularities form, these things just shrink to 0 and the result is not applicable. Okay, so that's a little bit of a just general overview about quantitative stability estimates and quantitative estimates for critical points. So let me try to find where the cleaning thing is. Yeah. So let's now turn to the problem of the Dirichlet energy. So actually this, sorry, seems I'm not quite awake rather than the audience. So indeed this work of Simon on Wojciechowicz estimate was very much motivated by geometric variational problems, namely by the study of harmonic maps and of minimal surfaces and the behavior of tangent cones for minimal surfaces. And so the problems I'm interested in is just the classical Dirichlet energy for maps from surfaces, where there's a huge amount known at the level of compactness theory, regularity theory, all of these things, but surprisingly little is known about quantitative behavior. So let's turn to this, and let me just introduce a bit of notation. Okay, so I'm going to consider for all of this the Dirichlet energy u 1/2 integral grad u squared dvg sigma for maps from a surface sigma g into a Riemannian manifold ngn, where these are, so this is two-dimensional and they're both closed Riemannian manifolds, respectively a Riemannian surface. And I can, of course, then just without loss of generality assume this is a subset of some huge Euclidean space. I'll call this n, but k. Now let me recall a few basic properties, even though I might be copying some other people's work and talks. We have quite a few talks about harmonic maps. I hope nobody minds. So let me just recall what we know. So for this energy, the set of critical points, these are harmonic maps. And they're characterized, and that's important for sort of trying to use this machinery of Wojciechowicz estimates, they're characterized by a nice elliptic nonlinear PDE. So they're satisfying Laplacian of U, or rather I'm writing their L2 gradient of the energy can be written as minus this gradient is Laplacian U plus second fundamental form, grad U, if I'm viewing the map as a map from a surface into the corresponding surrounding Euclidean space. Let me also remark that the Dirichlet energy is closely related to the area. So we have the energy of any map is bounded from below by the area of map taken with multiplicity, so literally the integral of ux1 wedge ux2 when I take local coordinates with equality if and only if u is weakly conformal. So it preserves angles, but it's allowed to have points where the gradient vanishes. And so this just is a consequence of Cauchy-Schwarz applied to this side being bounded by ux1 squared plus ux2 squared and a half of it. So this is really useful, in particular, if you look at the case where the domain sigma is the sphere. So let me remark that in this case, that if, so if sigma is the sphere, then U harmonic implies U conformal. So in this special case where you go from domains from the sphere, then you get the same thing. You get the area of harmonic maps is the same as the corresponding energy. And let me also remark that because if you're in 2 dimensions, this energy has a nice conformal invariance. So if you change the conformal factor of the domain metric, this doesn't change the energy at all. So you have a conformal invariance. And in particular, if your domain is the sphere, you can just as well think of maps from R2 instead of S2. That's the same. Singularities can be removed in that case. And in particular, if your domain is S2, then your symmetry group is quite nice. It's just the Möbius group on the domain, which basically pulling back by Möbius transforms doesn't change anything. Okay, so in particular, as a consequence of the case of the sphere, if you are looking at critical points, so if I look at the energy spectrum of harmonic maps, calling this psi of n, u from S2 to n harmonic, then this is the same as the areas of minimal spheres. So possibly branched minimal spheres. And now most people really object to the sorry?
Energy is in the first one, not
yes, thank you very much. E of u, yes, absolutely, yeah. Now, most people object to the use of the letter big psi because they think a letter should not be having multiple connected components. And I have always objected to the use of letter big psi in any paper with any collaborator, and I've always won. But actually, in that instance, I quite like the letter big psi. And this letter is connected to a big conjecture of Leon-Simon, which says that the letter big psi is the right notation. To be more precise, there's a well-known conjecture which goes back to Simon and also Francois Lin. So this is in the 90s. And this conjecture says that if n is analytic, then psi n is discrete. i.e., if you think of your energy levels, and that's quite an intuitive thing for physical energies, if you think about the energy levels of your critical points, there's gaps in there. Okay, so what is known, or what was known back then? So known back then, I should say, is basically part of the psi is okay. And so first of all, we know that the first level, the first interesting level, I'm calling this E star of n, defined as the infimum of E of, of psi n without 0. So this is actually is achieved and is isolated. So like the first level that's of interest here has a gap to the next guy, that's for sure. And then the other thing which is known is that any candidate, so any potential accumulation point, E bar, say, needs to be of the form that E bar is equal to the sum of j is 1 to n, where n needs to be strictly greater than 1, so there needs to be at least 2 of these energies, energy of omega I, where omega i's are harmonic maps again. Harmonic, not constant. So basically, the next guy can be built out of the previous guys by building it up. Just, for example, by adding things together. That's possible, but an accumulation point needs to be of this form. And the sort of background behind this is the compactness theory for almost harmonic maps that was developed through the 90s, which has to do with the bubbling theory of harmonic maps. So let me recall a little bit about this. And yeah, I should of course say there are situations where this thing is just known. So if you are looking for maps from S2 to S2, and this psi of n is simply multiples of 4 pi, hence it is discrete. If you are looking at maps into something non-positively curved, there are no non-trivial harmonic spheres, so the thing is just 0, therefore it's discrete. But in terms of more general the target manifolds where you don't know the exact energy spectrum, that's basically what was known back then. And so let me just draw a few pictures. I think I might even have colored chalk. Colored chalk. So what's the reason? So the reason behind this is the compactness theory of almost harmonic maps. So basically, if you know that ui go from any sigma to any n, which have bounded energy, and their gradient goes to 0, then what happens is that the ui's will converge to a, say, omega 0, a base map, which is harmonic. And this is weak H1, but it is strongly, so this is weak H1 everywhere, but it's strong H2 away from points. So a singular set, which is just a finite number of points. And then near these points, you have bubbling. So if this is your domain into n, if you have such a singular point P here, then what happens is that if you look at your ui's, there will be energy concentrating on smaller and smaller scales. So in applications, you might call them microdomains where something happens. And there might be multiple of these domains. So you can have like a little ball here where if I zoom in and I scale this up to unit size, then you're going to get another map, omega 1, which is a non-trivial harmonic map from R2 to your domain, your target. So R2 to the target is the same as S2. So it's a bubble. That's what a harmonic map from the sphere to your target is often called a bubble. But then you might have an even more concentrated scale. Well, let me just do that with orange. So basically, you might have another little domain here. And if you zoom in here, you're getting yet another domain and yet another map, omega 2. So you can sort of think of this here as what's happening is you have an outer tiny scale. So this is a R1, really, really small. And then you might have more concentration points. And you can have towers of them. You can have so-called bubble trees. And at each scale that you zoom in, and they're really different, the corresponding quotients of the radii, they will go off to 0 or infinity, depending on how you norm it. And you can extract the bubble all the time. And now what the compactness theory tells you is that this is all that happens. And so if you account for all of these bubbles, you can actually write ui minus the base map minus the sum of bubbles as something that goes to 0. So what you get is if you sum up the bubbles, so you have omega I, they will come really concentrated around some points. Some points, let me call them xi. So you have x minus xi, they come at really, really small radii, so I have to divide through ri. And if I do this the right way and normalize by taking away the limiting thing, then this goes to 0 in H1 and L infinity. So basically your whole map is built out of puzzle pieces, some of which are coming at extremely small scale, and then the bulk map omega 0. The problem with this result is while it's beautiful and it converges in the best possible way, it does not tell you at all like how close you are to such a bubble tree. And in particular with regards to my warm-up example, so one of the things I mentioned is that this constant that you get in estimates depends on eigenvalue gaps. And the neighborhood where you can expect this to hold true also depends on eigenvalue gaps. And if you look at maps like this, the relevant non-zero eigenvalues, they shrink to 0. And that in practice means you cannot do anything. And that means that therefore the classical results, all they give you is when you converge to the infimum, because in that case you either don't have any bubble forming or you have a bubble forming on a trivial base map. And then you just say, oh, well, that's a silly way of looking at it, because I have Möbius transforms, which give me a symmetry group. So if everything concentrates at one tiny scale, a Möbius transform scales things up to just unit size again, so it's not a singular setting. So in that case, you can do this. And you know that that's the bubbling is the only thing which could go wrong in the classical way. So if you have an accumulation point, it needs to come from bubbling, but you do not know whether that actually can happen. Okay, so we're now in the 90s, so we've advanced from the 80s, from Simon's result to the 90s of the compactness result. So let's now see what we can do in the next, 20 years in terms of progress on this conjecture. And similarly, so what do we have in terms of progress since then? So there's been some progress on Wojciechowicz estimates in singular settings, or in the presence of singularities. In particular, there was work of Peter Topping from 2004, and recently by Waldron 24 for maps U from the sphere to the sphere, and there the first and the second inequality are okay. And then there's some more results on related problems. So we have on optimal Sobolev embeddings. So there's work of Figalli, Glaudo, from 19, and then from, let me just get this right, then Sun Wei, who generalized the results of Figalli to higher dimensions, I think 18, 19. And then there's work on mean curvature flow from Kolding, Minicozzi, and Chodor-Schulze. And that's pretty much it in terms of Wojciechowicz estimates in the presence of singularities. So there's very few results like that. And at the same time, when you think about progress on Simon's conjecture,
which kind of exponent one gets in the presence of the singularities?
So here, the best one for the sphere. Here in Figalli-Glaudo, in the low dimensions, you get, again, the best one. In higher dimensions, you get a smaller one. So what they proved is that in the lower dimensions, you get the full gamma equals 2, in particular for the energy one. But they also proved that it can't be true in all dimensions. And then Deng Sun Wei proved the corresponding exponent in higher dimensions. Yeah. Now, progress on Simon's conjecture. At the same time, if you compare just with this list, the only thing related to the Dirichlet energy is the work of Topping and of Waldron, but that's S2 to S2, where the energy spectrum is known anyway, so there's literally been no progress at all. And basically, you just do not know how to do things. On the other hand, well, it's an intuitive conjecture, and we would actually like to know about it. So I at least have some progress to report. So let me cross this out. Just some progress. So from about a year or two ago. And this result is that if n is a three manifold, such that the minimal energy bubbles are nice. So they should be not branched, which is pretty intuitive, and they should be non-degenerate. Then the first candidate for an accumulation point, which is the first time you get a sum of energy, so it's 2e star, is not an accumulation point of the energy spectrum. In particular, really, the next one also has a gap. So psi, at least with 3 of these lines, is an okay letter to use for your energy spectrum. So you have these gaps. Now, so far, this result is restricted to basically settings where you have Wojciechowicz, where you have just a single bubble forming on top of a base map. But that's just because I cannot glue more complicated minimal surfaces at the moment. So I want to give a very, very brief idea of how we prove that, because it's quite different to how, for example, the result of Topping has been proven. So these results of Topping and Waldron are very much dependent on the special geometry, and they basically really use that maps from S2 to S2 are really special. They are related to holomorphic maps and so on. I'm going to come to that in I still have 20 minutes, is that correct? Yes. Yeah, okay, good. Sorry, I'm always ending up giving a slightly different talk than planned, but I guess that's okay. Right, so just a brief idea of the proof. So, and this goes back to joint work with Malchiodi myself and Ben Sharp from 2020, I guess, on arXiv, and this is on H-surface equation. So basically what we're doing is we're trying to reduce the idea of proving Wojciechowicz estimates to a much more hands-on problem, and that's a gluing problem. So what we're showing is that we can, step one is design, construct very careful models. Oops. So I'm going to call this big set, maps set, from S2 to N of bubble trees. So this uses really careful gluing methods. You take a map, a base map, you take a bubble, and you find a very specific way of gluing them together. And then you take these models and you go off and you carefully analyze the energy on this manifold. Oops, I shouldn't call this set because. And then you do not do anything more. So step 3 is be happy. And that means dimension reduction techniques give you what you want. And it gives you what you want without analyzing general. Basically, U from S2 to N. You never have to analyze the general almost solutions. You get everything for free as long as you construct the right set of models and as long as your energy has the right behavior. And so the key thing you need is basically this set of models of bubble trees. It needs to capture all directions where your eigenvalue gap shrinks to 0. So what you need is that d squared E is uniformly definite. I think this is not a good joke. Orthogonal to Z, not just capturing the null directions, but also capturing the shrinking to 0 eigenvalue directions, which actually forces you to glue a lot more maps than what you think you might have to. And then you need for all elements of Z, which are not critical points, there is a dominating direction in the energy expansion. So there's a sort of dominating repulsion force which tells you the reason I cannot glue two maps which don't quite fit is because I could reduce energy by shrinking the scale that they are glued at, turning things around, moving things, something like that. And so as soon as you have these two properties, you're fine. And it doesn't matter whether it's a Dirichlet energy or whether it's pretty much any nice energy. This method still is really designed to work. And what it gives you is Wojciechowicz estimates which hold on a whole uniform neighborhood of a non-compact set of models. So instead of having the problem that if you have these bubbles forming, so these models look very, very similar to these guys, but just with very specific gluing methods, and you're guaranteed that any map that's epsilon close to this is basically going to fall into a situation where the be happy applies. And morally speaking, what this set does is you're basically thinking, just take a hands-on model out. So you're basically thinking of, you have this infinite, this non-compact set of models. They are like a valley. They are not completely flat because they're not critical points. So they may be tilted a little bit like that. But the important thing is they capture all directions in which you don't look at like a parabola. So everything else looks like a parabola. And the be happy part is just to say if I have a general point, I'm basically looking for the nearest point down in the valley, where I understood everything because I'm explicitly constructing these gluing constructions. And then in this direction, it's literally just my simple example behavior. And dimension reduction tells me that it just looks like a parabola and life is good again. Okay. Yeah.
Connectedness of the space of solutions.
Sorry?
Do you get local connectedness of the space of solutions as a byproduct?
No, I wouldn't. I'm not sure. I haven't actually thought about this. So the manifold will have some points in there. Yeah, I guess you could. I would need to think about it more. Yeah. I mean, this is, in some sense, this situation is particularly interesting when you don't have any solutions, actually. So in particular, when you do these arguments, what you basically want to say is there are no maps which are truly harmonic, which look vaguely like that, and which have this bubble tree convergence. And so in that situation, you would have an empty set. There's other situations like maps where you actually approach a bubble tree that corresponds to exact harmonic maps. Then you would basically say that it's only a certain set of harmonic maps. Yeah. So you do get actually a sort of side product. You get a characterization of the true critical points as well. Yes. Yeah. Yeah. Right. And now I've lost my thing. Okay. So that was question 1. And I promised I would do a little bit. Well, I didn't promise anything. But let me just mention also a few more things about the second question I raised, namely about almost minimizers. So here I wrote up a short list of things which are known in terms of Wojciechowicz estimates in settings which have this sort of multi-scale behavior where different things happen on microdomains and on big domains. If you look at quantitative stability estimates for minimizers, the list is even shorter because there basically are no results which apply in true multi-scale settings. So let's just look at almost minimizers in the simplest setting of the Dirichlet energy, and that is maps from sphere to the sphere. So if I look at this, and I'm going to say they should have degree of U is k, let's say greater or equal to 0. So here we know that the energy of U is greater or equal to 4 pi k with equality if and only if the map is a conformal map from the sphere to the sphere. So it's given by a rational map. I'm calling this Rk, which are basically U of z equals a polynomial of z divided by another polynomial of z. If I view this S2 here as C hat, the holomorphic, complex extended plane using stereographic projections. So in this case, minimizers are simply meromorphic functions. The degree of the maximum degree of the polynomial corresponds to the degree. So therefore, we can ask whether, in this case, I can bound the distance of a map U from the nearest rational map in terms of the energy defect to some gamma for delta U is the energy of U minus 4 pi k. So that's the basic question of almost minimizing behavior. Now, first of all, k equals 0, yeah, of course, that holds because it's just the distance you want is the H1 map, and that's just coming from the energy, so life is good. That's just trivial. Then the first interesting case is k is 1, where, of course, rational maps are just the Möbius maps. And now what's special about this case is that the Möbius map is also the symmetry group. And that really helps you here. So what you have is, this is true with gamma equals gamma 3 equals a half with the optimal exponent. And that's a pretty complicated proof of people working on ferromagnetic films and skyrmions. Bernard Mantel, Muratov, and Simon originally. That was about 20 pages proof of this result, which was then thankfully simplified massively by both Hirsch and Costa Simas over there using method from elliptic regularization, and by Peter Topping using geometric flows. And the main thing here is really, it is in some sense a regular situation where everything happens on a single scale because the minimisers modulo the symmetries is just the identity, and the second variation of the energy is orthogonal to the Möbius groups is positive definite. And so you should expect, you still have to work quite a bit, but you should expect that it holds. And so what about higher degrees now? So higher degrees, the interesting part is that the set of critical point minimisers becomes non-compact even when you kick out the symmetries. So as soon as your degree is at least 2, you can have basically energy accumulating on 2 different scales, and the Möbius group is not strong enough to scale up 2 scales. You can scale up 1 scale, but that means you will then just basically mess up the other scale. So if k is greater or equal to 2, then the set of rational maps modulo symmetries is non-compact. And so a typical example is you're taking U of Z. I said we want meromorphic Z plus 1 over mu Z, where mu is huge. So basically this looks like the identity at scale 1, but then if you zoom in at the origin, or if I do the sphere, go down to C hat, I guess that would be tiny little ball on the origin, radius about 1 over mu, then at that radius, this thing looks like a 1 over Z, which is massively rescaled. And no matter what you do in terms of Möbius transforms, you cannot get that one to behave. It will always have a singularity in there. Now, near a fixed subset of that, fixed compact subset, life is still good. Because orthogonal to that, it still looks like a parabola, your energy. And actually, the result is just an adaptation of the regular case. You could adapt the proof of Topping and so on. So a local result is still true. And that was work of Deng, Sun, and I got the Wei. So these are the same people who generalized Figalli's result. So there's locally, i.e. epsilon close to critical to a compact subset of RK. It's still okay with gamma equals 2. Globally, a half. Globally, gamma is a half doesn't work, but what they conjectured in their paper was that globally we can bound the distance of any degree k map to the rational guys by c times delta u to the half. So the optimal thing with a small correction. And the small correction should have logarithmic form to the power of half. Now, if you look at the result like that, you would think, come on, no log in that thing. I mean, that just looks really wrong. But the thing which looks correct is, I mean, it's a nice energy, so the distance of a set to the minimizers should actually be bounded by some reasonable right-hand side. So you would expect it is true that the distance is bounded by some delta u to something, but maybe the log looks a bit wrong. And this is one of the fun situations where your intuition first is just the completely wrong way around. So the log is correct, but the estimate is completely wrong. So how does that work? So the estimate is completely wrong, not just at the quantitative level, but at the qualitative level. It is simply not true that if your energy is close to the optimal energy, that your map is close to a minimizer. This is not true at the convergence level, and the proof is actually very, very simple. So first of all, little observation. So this is in a paper from, I guess, on archive, summer before last. So we have delta, so for any k greater or equal to 2, delta u going to 0 does not imply that the distance of u to the minimizers goes to 0. And the example is second year undergraduate. It uses the Cauchy formula for complex analysis. So the counterexample is basically take one of your objects which are non-compact minimizers and destroy a key property of holomorphic functions. And the key property of holomorphic functions is that mean values over disks or mean values over circles is constant. And so the counterexample you can construct, you take uk of z is z plus 1 over mu k z, and then you transition from 0 away from 0 to 1 very near 0. And this is near 0 basically set scaling like 1 over mu. And you can do this with delta uk bounded by the logarithm. But the distance of any such guy from a meromorphic function is order 1 because it cannot match both 0 and 1 as a mean value over circles. Right, so it's wrong. And if something is wrong, it just means we're not studying the right problem. And so this is where my talk finally gets non-Riemannian, I guess. So the thing which happens is that you're comparing with the wrong type of objects. And the exact minimizers, the regular exact minimizers, are far too rigid for a problem which is like a multi-scale problem. So the right thing to do is to basically say, my object looks either like a meromorphic function of the given degree, or I must have energy concentrated at a massively, massively small scale. And on each relevant scale, it looks like a meromorphic function. But these meromorphic functions might not be related with each other. In particular, they might not have the same asymptotic value. And so what you can say is that the right limiting object, the right sort of generalized minimizers are rational functions of degree k and collections of rational functions omega 1, omega n of total degree equals k living on extremely different scales. And in particular, allowed to have different asymptotic values. So morally speaking, I think of this as, here's my set of rational maps, here's infinity, and instead of putting a single point here, which is like the singular objects that I get, the weak limit, I actually have to expand, and I have to expand more extra elements which have more extra dimensions, which are comparison objects. And now what you should think about is basically any u that you have will be close to one of those in a way that measures the right norm, the H1 norm, and that measures how far off from infinitely concentrated the thing is. And that actually works. And so the result here, and I'm going to just state this vaguely, is that for every k, we have that the distance of u to the set, these collections of degree k rational maps in H1 is bounded by delta u times log delta u, always a factor half, And this is indeed the best possible thing. So this is sharp. With this, I want to thank you for your attention and patience.